All right, I think maybe we need another example of this. Okay? Let's quickly review this idea before we go on to some other things. Let's pick a different n. N equal to 5, say. So we're looking at Z5 in a different way. How is it different? Well, I'm not thinking of its elements as being numbers. Okay? I'm thinking of its elements as being equivalence classes under congruence mod 5. That's the big conceptual hurdle to get over. The elements in this set, this collection of equivalence classes, which I could call A if I wanted to, consists, for this example, of 5 things. These 5 things. These are not numbers, these are equivalence classes, they're sets. The elements of this set are sets. But I can add these sets, I can define an addition on these sets. For example, the equivalence class containing 3 plus the equivalence class containing 4, what does it equal? It is in mod 5 arithmetic, and that rule at the bottom says you can first figure out 3 plus 4 to get 7, and then reduce that mod 4. What's the remainder, or mod 5, excuse me. What's the remainder when 7 is divided by 5? It's 2. This is the same as the equivalence class containing 2. And when I label these with something different, with some bigger number, for example, it's just a different labeling. In mod 5 arithmetic, this equivalence class is the same as this equivalence class. These are just different representatives of the same equivalence class. And this one is the same as, for example, this. And so I could do a calculation like this. I could use different representatives, but you do get the same thing in the end. Again, we're doing mod 5 arithmetic now, so 17 divided by 5 has a remainder of 2. I could write it like that. Or I could reduce these mod 5 right away. I could do it this way. I could go from here up to there and get the same answer. It's a different way of looking at the same group. Z5 and this group really are in some sense the same group, even though we're thinking about them differently. They are what's called isomorphic. Isomorphic. And that's a really important concept in group theory. All right, I'm going to go over the next few slides pretty fast. It's just basic number theory. I want to get on to doing some important kinds of proofs. So we quickly just review the division algorithm. You got 2 integers A and B. Say B is positive. Then the division algorithm, which again is not really an algorithm, it's not really a procedure, it's really a theorem, says there exists unique Q and R. They are unique with respect to the property that R is greater than or equal to 0 and less than B. You can find other Q's and R's that don't satisfy that condition, but with respect to that particular condition, that R is not negative and it's less than what you were dividing by, B is the thing you're dividing by. With respect to that condition, it's unique. Terminology, dividend, divisor. When you're doing A divided by B, A is the dividend, B is the divisor. Again, I often forget that, but I shouldn't from now on because it's in alphabetical order. Dividend, divisor. I just noticed that the other day. Q is the answer, so to speak. The quotient, R is the remainder. When you wrote this in 4th grade, you wrote it like that. If R is 0, that's very important. More terminology, you say B divides A, or B is a factor of A, or A is a multiple of B. We'll usually say B divides A, and write that kind of thing. But this is confusing. We were doing A divided by B here. But when you get a remainder of 0, you say B divides A, and you write it that way. So, for example, 3, for example, divides 18. But 18 does not divide 3. You can write both of those kinds of things. When you take 18 and divide by 3, you get a quotient of 6 and a remainder of 0. So 3 divides 18. And that's the thing I'll usually say. I usually won't I won't say these other things as much. Okay. Primes and composites you've seen before. Fundamental Theorem of Arithmetic is what was up your quizzed on. Prime, again, is any positive integer greater than 1 whose only positive divisors are 1 in itself. You've known that maybe since 4th grade. Maybe 5th grade, I'm not sure. Well, I always tell a little story. I think there was a hole in my education based on my memory. Maybe my memory's faulty. I actually, in elementary school, don't remember the day we talked about primes. I mean, we should have talked about them for more than one day, so my memory must be faulty or something. Because I remember when I got to college, I was like, what's a prime? Here I'm a math major, and I was forgetting what a prime was. Okay, I probably didn't miss that day, I just probably forgot it. Positive integer greater than 1 is not a prime, it's called a composite, and officially speaking, 1 is neither prime nor composite. And the reason you say 1 is neither prime nor composite is so the fundamental theorem of arithmetic is easier to state. That's why you say 1 is neither prime nor composite. So this is much easier to say. You could modify it if you counted 1 to be prime or composite, but it would be much more wordy. Every integer greater than 1 is a prime or a product of primes. I guess the author is thinking of this as an exclusive OR. A prime, like 7, is not a product of primes. Well, you could think of it as a product of primes, like 7 is 7. I guess you're not really multiplying there, so that's really an exclusive OR. It's a prime or something else, or a composite, it's an OR. And when it's a composite, it's a product of primes. This product is unique up to reordering the factors. And then we have the idea of the GCD. What I want to do now, though, is I want to prove not the entire fundamental theorem of arithmetic, but the existence part. I'm going to skip the uniqueness part. This proof is actually in the book, but I think it's worth doing. I'm going to use not the first principle of mathematical induction, but the second principle of mathematical induction. So again, this is all in the textbook, but I think it's worth going through. What does the second principle of mathematical induction say? It says, suppose S is a set of integers containing the integer A, and I guess, again, like I mentioned before, A theoretically could be negative. It doesn't have to be 1 or 0, but usually it's typically 1 or 0, or maybe even 2. Suppose S has the property that n belongs in S. This is different than last time. Whenever every integer less than n and greater than or equal to A belongs to S, then S contains every integer greater than or equal to A. Can you think of this in terms of dominoes as well? Well, you'd still need to verify A is in the set. So that's like knocking down the first domino, the base case. Last time we assumed that given an integer n, that for some integer n, the set had the property that when n is in the set, then n plus 1 is in the set. Essentially meaning, for any given domino, the next domino is sufficiently close to be knocked down when the first, that previous one falls down. Here you're really saying that given any n, like say the 10th domino, or wherever that is, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10th domino there, this has the property that as long as the first 9 dominoes fall down, the next one will fall down. That's essentially what you're saying. It's not just dependent on the preceding one, is the idea. If that property is true, then S is going to contain every integer greater than or equal to A. Let's go ahead and apply this to the proving the existence portion of the fundamental theorem of arithmetic. Fundamental theorem of arithmetic, not algebra, even though this is algebraic structures. It was the fundamental theorem of arithmetic because we're talking about number theory here. Fundamental theorem of algebra is related to roots of polynomials. We'll talk about it later. you could say let n be an integer greater than 1. I need to, by the existence portion of the Fundamental Theorem of Arithmetic, I need to show that it's either prime or a product of primes. Well, if it's a prime, we're done. So assume it's not a prime. If n is prime, we are done. So we only consider the case not doing this as a proof by induction yet. Sorry. Okay. Sorry, this is bad. Cross it all off. I was getting ahead of myself, okay? Getting to the last part of the proof too quickly. We were doing this as a proof by induction. You could say, let S be the set of all positive integers for which the FTA is true. And it would have to be bigger than 1, such that FTA, Fundamental Theorem of Arithmetic, maybe I should call it FTAR there like that, to distinguish it from the Fundamental Theorem of Algebra, is true. Theoretically, S could be empty, but it's not. It's going to contain all positive integers greater than 1. But the base case we want to show is that 2 is in S. Well, that's easy. Since 2 is prime, 2 is an S. It's a prime or a product of primes. It is prime. Now let's say let n be an integer greater than 1 and assume this is the inductive hypothesis. I'm not bothering to label the base case an inductive hypothesis this time, but this is it. Assume every integer k with this property is in S. Suppose S has the property that n belongs to S whenever every integer less than n and greater than or equal to a, which is 2 in this case, belongs to S. So if I can show that this assumption helps me conclude that n is S, n is in S, then I can apply the second principle of mathematical induction to say that S contains every integer greater than or equal to 2. And that would be finishing the existence portion. I can now say if n is prime, we are done. I can apply the second principle of mathematical induction in that case. I won't say it until the end, though. Well, maybe I shouldn't say we are done. Maybe I should say it like this. Then n is in S. If n is not prime, it is composite. Doesn't need to be said, but you can put it in parentheses. Then what? Well, what does it mean to be prime again? It means you are a positive integer greater than 1 whose only positive divisors are 1 in itself. N is a positive integer greater than 1. If it's not prime, it must have some other divisor. It's composite. it's got some other divisor. There exists A and B in Z with the property that they are both strictly between 1 and n, such that n is A times B. Because it's not prime. N is not prime. And they would have to be bigger than 1. Because if one of them is 1, then like if A was 1, then A times B could not possibly be n. These are both definitely less than n, since their product is n. But now use your inductive hypothesis. Again, in induction proofs, you always have to use the induction hypothesis. Use that assumption. How? Well, A and B satisfy this condition. They are in S. They are primes or product of primes. But n is A times B, so n is a prime or a product of primes. Actually, it's got to be a product of primes. And that's how you would finish the proof. Is it okay if they don't write it? It's in the book. You'd say, by the assumption, A and B are both primes or product of primes. Therefore, n is really a product of primes. Therefore, n is in S. And therefore, by the second principle of mathematical induction, S contains all integers greater than or equal to 2 in this case. And that proves the existence portion of the Fundamental Theorem of Arithmetic. Primes are pretty interesting. You might wonder how many primes are there. You ever seen this before? How do you say it? Sieve or sieve? Sieve. Okay. The Sieve of Eratosthenes, I think is how you pronounce that. Ancient Greek guy. To find primes. Start with 2, circle it, it's got to be prime, but cross off every multiple of 2, cross off every even number, those are the blue x's. Those are therefore not prime. Then circle 3, it's got to be prime because it's not a multiple of 2, but cross off every multiple of 3 that hasn't already been crossed off. 6 has already been crossed off, so cross off 9. 12 has already been crossed off, although I guess they made green there anyway. I don't know why they didn't bother to make the 6 green, but they did make the 12 green. I don't know. This animation I got off of Wikipedia is evidently not perfect. 4 has been crossed off, 5 is not. Circle that, that's the next prime. Then cross off all the multiples of 5 that have not already been crossed off, which would include, for example, 25 would be one that would not already be crossed off at that point. Etc. Go to 7. A new thing to cross off based on multiples of 7 would be, 49. Would be a new example of something crossed off based on being a multiple of 7 that's not already been crossed off. The things that are circled are the primes. You do see primes are pretty close together at first. These are only 1 apart, these are only 2 apart, these are 2 apart. 7 to 11 is 4 apart. 11 to 13 is back to 2 apart. 13 to 17 is 4 apart, but as you go further down, they get a little further and further apart in general. Sometimes they're still close together. For example, 97 is the only prime in the 90s. The distance between 97 and the previous prime, 89, is 8. Okay? In general, they get further apart. They get so far apart that eventually there are only finitely many primes. But, well, I didn't write it down, but actually, you'll never run out of primes. There are infinitely many primes. The proof of that fact is considered to be the most beautiful proof in all of math by many mathematicians. For sake of time, I don't really have time to write it out, though you can write it out in about 5 sentences or so. Let me give you the idea of it. I would encourage you to look it up. It's a proof by contradiction. Suppose that there are not infinitely many primes. Suppose there's only finitely many. Call them P1, P2 through, say, Pn. And consider the number n that is the product of all those numbers, of all those primes, plus 1. This number is bigger than all those primes, and since I've listed all these primes, this number must be composite. Because I've listed, it's bigger than all the primes, and I've assumed that I've listed all the primes. So this number must be composite, and therefore it must, by the fundamental theorem of arithmetic, have a prime factor. But what could that prime factor be? Could it be P1? Write the equation this way. Could P1 be a factor of n? Well, if it were, then n would be P1 times something, call it k, and you'd be able to factor a P1 out of this, like this, and say P1 is ultimately a factor of 1. What? How could a prime number be a factor of 1? How could it divide 1? That's a contradiction, so P1 must not be a factor. Could P2 be a factor? Do the same kind of thought process. There would be some number k so that n is P2 times k, and this same kind of thing would again lead to a contradiction, saying P2 divides 1. It's impossible for a prime to divide 1. Same thing would happen with P3, same thing would happen with any of these primes. Therefore, n cannot be composite and it cannot be prime. That's a contradiction. Therefore, the assumption that you had all the primes here in this finite list must be false. There must be infinitely many primes. All right, strongly encourage you to think about that some more. Maybe look it up. About a 4 or 5 sentence proof, you prove something very profound. There are infinitely many primes. You're never going to run out of primes, which is a really good thing for cryptography, right? Because it's based on primes. The fact that there's infinitely many primes will never run out is actually good for internet security, okay? That fact about prime numbers. Got only a few more minutes here. Again, this day has been mostly review, but I think it's good review with some more details and some more proofs. This GCD is a linear combination theorem, I know, is kind of strange to people. But it's actually really useful. Let me end class by illustrating its use to prove something else that's also useful. And that is called Euclid's lemma. If P is a prime, and it divides the product A times B, then it must divide either A or B. Symbolically, you can also write that like that. Lemmas, the word lemma basically means theorem, though often it's a theorem useful for proving other theorems more than anything else. It's sort of where the origin of the name lemma comes from. Before I do the proof, I should quickly remark that this is not true if P is not prime. For example, 6 divides 12, which is 3 times 4, but 6 does not divide 3, and 6 does not divide 4. But Euclid's lemma does not apply to 6 because 6 is not prime. So once again, That would be a counterexample to this statement if we did not assume P is prime. Again, if we did not assume P is prime, it's not true. It's not a theorem or a lemma anymore. P being prime is essential to the truth of this. And we'll see how so, hopefully, here in the proof. So set it up. Suppose P is prime and divides A times B, but let's say it does not divide A. The goal is ultimately to show it divides either A or B. To show that one thing or the other is true, it is okay to use the technique of assuming one of them is not true and showing that the other one must follow. And the case where B does not divide, or P does not divide B, would be equivalent. There would be the same proof. So I can get away by making this assumption and showing that P divides B. We must show P divides B. That's the goal. This seems difficult. If you were trying to think about this from scratch, or I were even, it might be really not clear how to go about doing this. How is the fact that P is prime relevant, for example? Maybe you try thinking about prime factorizations, and I think you could think about it that way. However, you can also use the GCD as the linear combination theorem. And one of its corollaries, actually. Here we go. Two non-zero integers A and B are relatively prime if and only if there exist integers S and T making this linear combination equal to 1, the GCD of these two relatively prime integers. P is a prime, and it does not divide A. P is not a factor of A. So P and A have to be relatively prime. This corollary applies. That comes from the GCD as a linear combination theorem. I'll just say by the GCD as a linear combination theorem, there exists S and T such that AS plus, careful, not B, but P, T equals 1. P is playing the role of B in this corollary to the GCD as the linear combination theorem. You can finish the proof essentially by multiplying both sides of this equation by B. Therefore, A times B times S plus P times B times T must equal B. That basically does it, because P certainly divides this. P divides this. It's a factor of that. And I'm assuming P divides A times P times B. P divides this. There exists, if you like, a K such that A times B equals KP. I can go ahead and substitute that in the equation to write it like this, and I can factor the P out to write it like this. Therefore, P divides B, and that does it. Okay, this is the proof that's in the book with a little extra explanation here. Can you see all this, by the way? Okay. With a little extra explanation. It's worth studying. I could see putting a proof like this on the exam, the first exam. So make sure you study that, think about it. It's an example of an application of the GCD to the linear combination theorem. All right, see you on Wednesday.